the last time we dealt with sinusoidally varying things was in 201 when we talked about oscillation. And our textbook presents oscillation by comparing the back and forth motion, say, of a mass on a spring, and comparing that to circular motion. The gimmick was that circular motion really just looks like back and forth motion. So we could use a projection, a shadow of circular motion. And have that represent motion back and forth. I mean, it's interesting, right? It's hard to tell whether I'm just moving my hand back and forth or whether I'm moving it in a circle. Because the circular motion is being collapsed onto the plane of the screen. That projection onto the plane, that's what we talked about when we talked about oscillation. We said that there's an imaginary circle with a very particular omega and a very particular radius. And that circular motion makes a shadow, makes an X component that looks like the oscillation we're trying to describe, the sinusoidal behavior we're trying to describe. And that makes me think that we can do something similar here. We have all these sinusoidally varying things behind me. Maybe we can represent them with some kind of circular motion and like reduce everything to the X component, like we did for oscillation. In every of these drawings, the current is a straight up cosine function. Starts at 1, -1, back to 1. It's a cosine function. Okay. It has some amplitude, but it's a cosine function. Has some amplitude, cosine. The potential difference across the capacitor, well, that's a cosine. This looks like a sine to me. Starts at 0, goes up. Has some amplitude. Not sure what. Looks like sine. 2 by ft. The inductor, now I erased it, but that function looked like this, which looks like the opposite of that. It looks like negative sine. Some amplitude, I'm not sure. Last but not least, the resistor. Now, if the pink curve is a cosine. The red curve is a cosine also. It just has a different amplitude. The way you keep track of this is to use something that we call a phasor diagram. It's the x-axis we care about. Let's start the picture at time 0. Now, at time 0, cosine of 0 is 1. So the thing that represents the resistor it's just here on the x-axis. Because the x-axis is representing the current right now value of the potential difference across the resistor. As time goes on, this argument increases, and we end up moving the angle that it's associated with counterclockwise around the graph. Eventually, we get to a point where cosine of something is 0. And at that point, the potential difference across the resistor is the x component. Cosine of 90 degrees is 0. Spin it, keep spinning it, becomes negative, 0 again, back to positive. Now the current is doing the same thing. Those are really similar colors, aren't they? Let's see if we can make that a little bit different. I think it's got to be purple. Sorry. That's different enough. The length of this red arrow is V sub r sub 0. Its current value is the x component, which is V sub r sub 0. I'll draw that in a second, but I just wanted to get the initial when t equals 0. T equals 0. Now, the sign of 0 should be 0. We're talking about the x component. The y component, though, should be negative. Let's think about this. Eli, the Iceman. The potential difference across the inductor should lead the current. Ah. In order to be a sine function, it's got to start at 0 and then go negative and then come back up and then go positive. We're tracking x components though. In order for that to work, we have to start it here. Current is 90 degrees ahead of, the potential difference across the inductor is 90 degrees ahead of the current, ELI. For the capacitor, current leads the voltage. Okay, so that just sets us up with the initial conditions and the orientation. Now, take the whole thing and start spinning it. Start moving it through circular motion with angular velocity omega. Sometime later, you've got an angle theta. What does the picture look like now? It's the current. The current from the source, that's what pulls us all around. Take I, move it through an angle theta. Let's put it here. This length is I0. The hypotenuse of this triangle that you're already thinking about. The angle that we're talking about is theta, or 2 pi ft. So it's all the x coordinates that we care about. It's all the x components. The current phasor doesn't point this way anymore. It is rotated. It is rotated theta degrees. It's x component now. It's x component. Is this slightly shorter thing, the original length that came out to here. That x component of the current phasor, this represents actual I, actual current. As the argument increases, cosine started at 1 and starts to decrease. The x component, as we rotate, starts to decrease from its largest possible value through to 0. I, as a function of time, is the x component of the current phasor. When we rotated the current, we had to rotate the resistor as well, because the current and the resistor are in phase. Whatever the current does, the resistor does too. The length of that arrow is the amplitude, VR0. Its x component is the value of the potential difference across the resistor at the new time. We can't only rotate these two though. We got to rotate the whole system. The inductor started here, and we're going to rotate it through the same angle theta. Same angle. Notice that the current and the voltage are still perpendicular because the voltage leads the current by 90 degrees, by a quarter period. The length of this arrow is the amplitude. VL0. Its x component is the voltage across the inductor at this instant. We're almost done. We also had to rotate the capacitor phasor through an angle theta. The length of the phasor is the amplitude, V sub C sub 0. Notice that the capacitor voltage and the current are still perpendicular because the current leads the voltage for a capacitor by 90 degrees, quarter period. The x component the x component of the capacitor phasor is the value of the potential difference across the capacitor at this time. And as time goes on, we take let me see if I can do this with markers. Blue, purple, green. Blue and green are opposite each other. Purple points this way. As time goes on, we continue to rotate the whole assembly counterclockwise. At any time, if we want the value of the potential difference across that element, we ask for the x component of its phasor. The circuit we have is an alternating source. And it doesn't matter the order. We have a resistor, capacitor, an inductor, and we're back. If we apply Kirchhoff's rule, suppose we apply it this way. The potential difference across the battery going this way. We lose some in the resistor. We're going this way around. We lose some this way in the capacitor, this way in the inductor. It all has to add to 0. In other words, the potential difference across the source is the sum of the potential differences across the pieces. So this red vector here, the x component, we said that was V sub R. So that's one of them, VR. Here's VL. Here's VC. Add them up. We get the voltage of the source. At that instant. There was a moment at the beginning when the inductor pointed straight up and the capacitor pointed straight down. Their x components was 0. In that moment, the potential across the source was equal to the potential across the resistor. Does that mean that's the amplitude of the source? No. How do we find the amplitude of the source voltage? We can find it if we recall formulas from the previous segment about reactants. These amplitudes are related to the reactants of those elements. Remember, write it here in this voltage relationship. The reactants in the deal for a resistor is nice. It's just the current times the resistor. The resistive reactance is just R plus the capacitor, the reactance, potential difference across it, we said, to do like an Ohm's law thing, was the current times the reactance, which was 1 over, well, let me just write it as X. XC. And the voltage across the inductor was I times XL. I can't write this equation. I mean, it's a nice enough place to put the reactances to remind us that we know them. But this is the peak or the RMS. But the peak voltage across the resistor doesn't correspond to the peak voltage across the capacitor. They don't happen at the same time. So I can't add them up and call that the instantaneous value of the amplitude of the source. I can't do that. I do know that I can't do that because they're out of phase. They don't all happen at the same time. I can't add them all up like that. Well, what do we know? We know that VR0 is equal to that. That the length of the resistor phasor is that. We know that the length of the capacitor phasor is that. And we know that the length of the inductor phasor is that. As long as we're talking about amplitudes, right? I0. And anytime we want to add up the X components. Okay. So, all right. So if we want to add up the X components, we're going to treat them like adding vectors. Like these kind of look like vectors. They're directed lengths. So add them together to find the resulting X component. Add them together to find the vector itself. All right. Adding 3 vectors is something of a trick, but we're helped out because we know that these two are opposite each other. So we could combine them. We could simplify things. We've got current resistor. The color I haven't used yet is orange. Somehow I'm putting blue and green together and getting orange. I don't know. To me, it looks like the blue is a little bit longer than the green. Together, there's a net this way. This vector represents VL minus VC. And it's perpendicular because, yeah, these are both perpendicular to the resistor. Now we've got two vectors. We can add them. We just put the one over here, and the result, add all these colors together, it looks something like brown. And the X component here is the instantaneous voltage across the source. The amplitude of the source is the length of that hypotenuse, is VS0. But we can find its magnitude because this is just a right triangle. This orange thing is perpendicular to the red thing because these two pieces were both perpendicular. We combine them, but the result is still perpendicular to the resistor phasor. So this is just a right triangle. So we can use what? Pythagorean theorem to find the length of the source phasor. Okay. VS0 is the square root of the square of VR0 plus this thing squared, VL0 minus VC0 squared. I'm going to math with this a little bit. I got to erase this. We're almost done. Let's plug in the expressions we know. ER0 is just I0 R squared. BL0, that's I0 XL minus I0 XC all squared. Let's factor out the I. And then we can square the pieces. So we've got I squared and this guy squared. Let's factor out the I squared. R squared plus XL minus XC squared. The square root of I0 squared, that's easy, we can do that. That leaves us with this thing, R squared plus XL minus XC squared. If we compare the form of these Ohm's law looking things to this, B equals I, V equals I, B equals I, B equals I, something else. So this thing, this radical expression, is like the reactance of the whole circuit. It's not quite reactance because we've got reactive pieces and just plain old resistive pieces. It's not quite resistance because we also have reactive pieces, so we make up a new name. Same idea. Call it impedance, and we use the symbol capital Z. So we can write the source IZ in a really nice pattern with the individual components. These reactances depend on the frequency with which we're turning the diagram. The faster we rotate, the faster I0 alternates. That's omega. In this diagram, we had rotated things through to an angle theta. Purple and red make an angle theta with the horizontal. The source phasor is at a different angle, generally. Different angle relative to the source voltage. Or, I'm sorry, the source voltage is at a different angle relative to the source current, or the current in the entire circuit. The function generator is a current source. That's the big news. The voltage across the source might be slightly out of phase with that, just because of the interaction of all the different pieces here. What is that angle? Well, it's, we could do some inverse trig, right? We could write, I'm going to erase this diagram for now. We could write that tangent of that angle is opposite over hypotenuse, or opposite over adjacent. V L 0 minus V C is 0 over V R 0. We could write that the cosine of that angle is adjacent over hypotenuse. Only resistors dissipate power. The capacitor, the inductor, those voltages are always perpendicular to the current passing through them. Current and the voltage are always out of phase, entirely out of phase with each other. They do not dissipate any power, only the resistors. What is the potential difference across the resistor amplitude compared to the source. And cross multiply. And this tells us the factor by which the power through the power dissipated in the resistors differs from the power supplied by the source. Some of the power that is being supplied is going to manipulating the electric and magnetic fields of the capacitor and inductor respectively. The power dissipated by the resistor is some fraction of the power being supplied. So this cosine phi, we sometimes call it the power factor. It's the factor by which the power dissipated by the resistor differs from the power supplied by the source. There's one more section in the textbook about resonance, that there is a frequency at which we can drive, a frequency at which we can alternate the current so that the voltage responses go as large as possible. There's a peak in the response. The RLC circuit lab will ask you to find this resonance frequency and just compare it to the formula that I think is given in the text of the lab. So that's the only thing in the section is here's the formula, and I can't say anything about it that won't be better explained when we go through the lab. So finally, I've reached the end of tonight's material. Thanks, everyone.